things. Now we have to search for the stuff, so we have a separate searching program. And this diagram is obviously getting very complicated. So what's interesting, you know, having lived in the developer world, developing these applications, and you know, like a lot of folks moving up this ladder into management and kind of larger picture architecture, inevitably, from a cost perspective, no offense to the developers, operations will always trump developers from a cost perspective. It is actually the case that OpEx, or variable cost, is always more costly than CapEx, or fixed cost, for developing an application. So with any large organization, enterprise-level organization, the deployed lifetime for any application is measured in years. So ultimately, the cost to maintain an application and the infrastructure an application is built on is multiplied annually by the lifetime of the product. And it's actually one of the reasons, the chief reason that I selected RIAK when I was at Columbia, and why it kind of resonated with me to a certain degree. Frankly, I'd rather spend money on developing features and extracting efficiencies than babysitting infrastructure. All infrastructure has to be babysat. The question is, to what degree? RIAK itself is based on this paper. This is the Amazon Dynamo paper from 2007. Very, very famous. It's one of the 4 horsemen papers of the NoSQL apocalypse, I like to call it. The other 3 were the Google file system, the Google Big Table, and the Google MapReduce. And those 3 papers are kind of the academic and philosophical underpinnings of the Hadoop ecosystem. And things that do big table-oriented stuff, like Cassandra's data model for super common families. Dynamo is a direct inspiration for RIAK. And actually, the paper came out in 2007, and I was at the first public announcement of RIAK, which was in the fall of 2009 in New York City NoSQL meetup group. And at the time, it was a panel between Couch and Mario, and one of the senior engineers for Basho, the original engineers on this product, gave a quick 5-minute lightning talk, and I was like, yeah, that's the one. He goes, that's the one that looks like this. And what was the problem that Amazon was trying to solve? They were trying to solve the problem of ensuring that they could accept shopping cart requests at all times. So Amazon was able to quantify how much money they were losing for every minute they weren't able to accept a shopping cart request. And consequently, they came up with this interesting design, and that's what they talk about in this paper, and that's what you see in production in the RIAK environment. Some of the things that I'm going to talk about in the next few slides are specific to that architecture and why it is that RIAK is highly available and operationally simplistic and all these fun things that we really like. A little bit on this and some key considerations for those of you in the room, which I imagine most of you have a tremendous amount of SQL and relational database background. This is a key consideration. And it has nothing to do with normalized versus denormalized structure, or structured versus unstructured data model, because that's at the data model level. What it really has to do with, and when I speak to folks about this, it really has to do with distributed versus not distributed. Relational databases generally are not distributed. RIAK in particular is distributed, and all data persistent systems are governed by the CAP theorem, C-A-P, consistency, availability, and partition tolerance. RIAK, Basho made the particular decision, considering our distributed nature, to have availability trump consistency. And so we like to refer to it as eventually consistent, because the way that we maintain high availability is through replication. And so we will replicate your data within the cluster some number of times. The default number of times is 3. And There's no magic here, so you can't magically say they all happen at the same time. All of those writes happen at the same time. So ultimately, the reason that we do this is such that in a RIAK environment, you can withstand any double machine failure and still maintain access to 100% of your corpus. And how do we do that? So in the relational world, how do you grow a relational system? You have a single machine, you grow that machine vertically, then you reach some kind of upper bound, and now you implement a master-slave architecture where you have writes going to the master and reads going to the slave or slaves. Then you take that unit, the master-slaves unit, and you shard your data across them. Inevitably, what will happen due to data access patterns is that one or more of your shards will be disproportionately accessed versus the others. And so, operations will have to come and compensate. And immediately what you've done by physically compensating for one or more shards versus their siblings is you've created an operational complexity. And this will have ramifications down the road at some point. RIAK takes a different approach. In RIAK, every machine in the cluster is identical. RIAK is a homogeneous system of identical machines. Each machine can do all the operations. Each machine can do every read and every write. And each machine is responsible for its own share of data and performance in the cluster. And how does it do it? So it has to do with data distribution. Whenever you shard a relational system, you have to shard on some dimension. Let's say time, or a customer last name, or who knows what. RIAK takes a different approach. RIAK shards by SHA, the SHA algorithm. And the output of a SHA algorithm is a number in the 0 to 2 to the 160 range, some really unfathomably large number. And but that's not the interesting part about SHA. The interesting part about SHA has a unique mathematical property called uniform distribution. So every time you put a piece of data through the SHA black box, you get out some number. But let's say, for example, you took two sequential pieces of data, let's say key number 1 and key number 2. They're sequential. But after you put them through the SHA, they could be anywhere along the number line, 0 to 2 to the 160. So uniform distribution is one of the key properties of RIAK. And it's distinctly different from normal distribution, or the bell curve. When you take two die and you roll them, and the numbers will cluster around the 7, because 7 is what comes up most often when you roll two dice. So that's a normal distribution, or the bell curve, but this has nothing to do with that. This is a uniform distribution. Uniformly distributing your data around the number line. So now imagine you take this number line, you turn it into a circle, 0 at the top, go all the way around the circle to 2 to the 160 at the end, and you subdivide these numbers into ranges. So we call that configurable parameter the ring size, and the default number of segments in the ring, which we call virtual nodes, again equal to the ring size setting, is 64. It's basically powers of 2, minimum 8, 10, maximum 10, 24, and in steps of power of 2, due to power of 2 division map into 2 to the 160. And this is, and what you get when you do that is equally sized segments. Some number of equally sized segments in the ring. So when you put it, what gets hashed? Recall, RIAK is a key value system. Key value is the data model, primary data model. Secondary data model is document. So when your value is a document like JSON or XML, then you can leverage searching, Solr, and I'll talk about that a little bit later. But the key itself is what gets hashed. And the key is a unique combination of a bucket and an ID. So for example, users/user ID, or transactions/transaction ID, something of this nature. So here we have artist/REM.
Hey Sasha, we're at the halfway point.
Okay, thank you. So that combination gets hashed, and that hash floats somewhere on the ring. The virtual node, for example, it might be hashed to virtual node 1. So internally, the replica set would be virtual nodes 1, 2, and 3. Let's say, for example. And virtual node is the key layer of abstraction in the RIAK system. It's not the physical machine. It's the virtual node, which in turn, amongst all the virtual nodes in your system, 64 by default, they're equally allocated to physical machines in the system. So let's say, for example, you had 100 virtual nodes, and you had 10 physical machines. Each physical machine would get 10 virtual nodes. So the virtual node is the key layer of abstraction in the system, and all data is written to the virtual nodes. Internally, RIAK knows where each of the virtual nodes are mapped to physical machines. And because of the uniform distribution due to the SHA algorithm and the equal allocation of the virtual nodes to physical machines, the way that you can think about the system from an administrative kind of macro level architectural perspective is that each machine in the cluster is representative of one end of the total data in the cluster and one end of the total performance. So again, if you have this hypothetical 10 physical machine cluster, you can reasonably assume that each machine is responsible for 10% of the total data and 10% of the performance. And this is very unique and very interesting, and resolves a whole host of issues from an operational perspective. When you can simply think of your cluster as a whole, and then each piece of the cluster carries its own weight, this becomes very interesting from a capacity planning perspective. How many operations do I need to service this use case? I need 100,000 operations a second. Each of my machines can do 5,000 operations a second. So how many of them do I have to put together to get to that number? This becomes very easy to start thinking about. So how does RIAK actually do all these things? RIAK itself is written in a language called Erlang. And Erlang is very well known for having certain unique properties. It was developed at Ericsson in the 80s, telecom. And it's the language that runs basically the entire world's telecom backbone, the heavy industry switches on the back end, the kind of things that can never go down, right? Because when Obama's got to call Putin, that call's got to get through, you know? So this is the kind of stuff that we're talking about, this kind of systems that run Erlang. And it was one of the key reasons that Erlang was selected as a language of choice for this kind of system. So what you're doing when you're creating a RIAK cluster is you're creating a fully meshed network of Erlang virtual machines. And what Erlang is especially good at doing is communicating amongst other Erlang virtual machines. So it's a fully meshed network of Erlang virtual machines that are continuously gossiping amongst themselves as to the state of the cluster at any given time. I'm machine 1 in the cluster. What does the cluster look like to me right now? Which machines can I see? Which machines can I not see? And it does this through the gossip protocol, and internally it's a tech that we call hinted handoff that determines which virtual nodes are living on which physical machines from my perspective right now. And what's interesting from an operations perspective is, of course, all of this stuff is happening without operator intervention. So there's no administrator sitting there telling the rest of the cluster, I just lost machine 1, recognize that, et cetera, et cetera. On the flip side of the high availability perspective, you have fault tolerance. So it's not really interesting how these systems operate when everything is good and you've got green lights everywhere. Green lights are boring. What's really interesting is when the lights start turning colors. And then you're like, what's happening? Am I gonna have to be up in the middle of the night to fix this problem? I know that I don't like to be up in the middle of the night. It's a problem for me. So I like to make sure that these systems are working for me and I'm not working for these systems. So we have hinted handoff, which handles issues during a failure. And we have these two mechanisms here to recover from a failure after you brought those machines back up. So the first is read repair. So as you read your data, you're repairing your data. It's exactly as it sounds. So if you recall, we do high availability in replication. So we would send 3 replicas down into the system, various machines in the system. And by default, we wait for a quorum to reply, 2 out of 3, which itself is configurable. Now what happens in this scenario? 2 replies will come back affirmative, and so that will service the request, and that affirmative will go up the chain back to the client. Yet the 3rd came back 404 not found. So what happens here? The coordinating node recognizes that the 3rd never came back. And so what it will do is it will take that copy from the 1st and 2nd and push it over to the 3rd. So the second time you make the request for a particular piece of information, it will be there in that 3rd place. Now that happens to data that you're actively reading. And it turns out, due to access data, again, data access patterns, the generic data access pattern is a Pareto distribution where 20% of your data is active at any given time and 80% of your data is cold. So what happens with the cold data? And for that, we have a system called active anti-entropy, which basically is a background process that generates a Merkle tree hash on the vnode layer. So again, going back to the vnode being the main layer of abstraction of the system, the vnode is responsible for a bunch of data. Data goes and gets written to vnodes, so the vnode owns the data. And then on a vnode by vnode basis, you're building this Merkle tree hash, and the system in the background continuously is comparing and doing a hash tree exchange. Comparing whether or not the data in the vnodes that are supposed to be part of the replica set are congruent. And if they're not congruent, it goes ahead and fixes it. So all that stuff is basically the underlying mechanics of how RIAK operates. And all of that stuff is open source. In fact, RIAK, you can go to GitHub and play with it right now. This is one of the key pieces that is an enterprise feature. It's closed source, but it's one of the key areas that we compete with a number of our competitors. Multi-data center replication. And what's interesting about the way that we do multi-data center replication is that we have the opportunity to create what I like to call hyper-flexible topologies. So you're a large financial firm, you've got data that you need to float from Asia to the Americas to Europe, etc. Or you need to follow the trading day from Tokyo to Europe to New York to Chicago. You can have clusters in each of these locations and connect them via real-time replication and also full sync, or like to call diff sync. So let's say you had a single cluster, and then at some point you brought up a second cluster, so you need to do a full sync first, and then you turn on real-time replication, and stuff just works. This is one of the key reasons that a lot of folks come to us and say, help us with this problem. What's interesting is that our approach is cluster of clusters. So you have a single ring, or a small concentrated ring in each data center. And what you do is you connect all these rings together in unidirectional fashion. So this is what also allows you to do these hyper-flexible topologies. You can have daisy-chained clusters, A to B to C. You can have fully meshed clusters, A to B to C, fully meshed all the way around. You can have hub and spoke clusters, or binary star, double hub and spokes in unidirectional in either direction, or bidirectional. And I've seen some very interesting topologies out there in the wild. One of our customers is running 3 100 physical node clusters, all in active. Not because they're running a petabyte of data, but because they have very tight SLAs as to when they have to be able to deliver that data to customers. And what's interesting about this approach is that with 100 physical machines, each machine is responsible for 1% of total performance. So when you lose 2, and this is the way that they went ahead and capacity planned, the 98 surviving siblings only have to absorb 2% aggregate performance. And even in this failed degraded scenario, they're able to maintain their SLAs. So these 300-node clusters, good stuff, good hardware, SSDs, all this fun stuff, but they have a 4th cluster. And the 4th cluster they use for analytics and archive. And this 4th cluster is not in the production pipeline. So it doesn't have to be as good. So this 4th cluster is actually only 20 machines. And instead of SSDs, they're running big-honking spinning hard drives. And they just use it for analytics and archive. So these are the kinds of things that you can do when you have this kind of architectural flexibility. Some of the things that are particularly very important to the developers is the consistency model. And I recall I mentioned availability trumps consistency. Yet, we're constantly pushing the boundaries on that. And so, beyond React being simply a key value-oriented system, we also have something internally called data types, which are production implementations of the academic space known as CRDTs, convergent or conflict-free replicated data types. And these aren't ints and strings. These are data types that are specifically designed to operate in a distributed computing environment. So for example, what do they bring to the table? What they bring to the table are automated conflict resolution strategies. In the regular RIAK KV model, when there is a conflict, either due to a concurrent write or a partition in the cluster, because the P in the CAP theorem is partition tolerance, which really means network partition. So if you have a 10-node cluster, it can be the case that the network partition become isolated. And these are some of the things that distributed database systems have to protect against. And it's something that we excel at. In a regular RIAK KV data model, when you have these kinds of issues, the system will not pick a victor automatically. We can operate in a last right wins scenario, which is the naive approach to conflict resolution in a distributed environment. And so it's the approach that some of our competitors take. And we can operate in that mode, but we highly recommend not doing that. Because the last right wins merge scenario is reliant on wall clock, actually real time. And for those of you who have distributed computation background, wall time is not something you can rely on, simply due to clock skew. The larger your distributed systems, the larger the likelihood that you will be affected by clock skew. So, let's say you have a logical write to side 1 of the cluster, and then another write, more recent write, to side 2 of the cluster, yet side 2 of the cluster internally, their clock is behind side 1. So all of a sudden, side 1 trumps side 2 in the last right wins conflict resolution strategy. And this is exactly why we absolutely recommend people do this. Instead, we use internal version mechanics known as vector clocks, another whole realm of academia we talk about for hours, but I will spare you. And just cut to the chase and simply say we use an iterative version of this called DVVs, dotted version vectors, that are a logical versioning mechanic internally that ensure that when you either have concurrent updates or divergent updates due to a partitioning, all of those updates will be preserved, such that when the next read comes in, that read will be presented with all the updates. And it's up to the developer to implement the appropriate merge strategy. And having been in this business for quite a bit now, it's not just myself, but all my colleagues who work on this system are convinced this is the only true way to do this, because if you're building a generic database, that means you're applicable to everybody and every use case. So there's no possible way that a system can make these choices for you. So what we do is we give you the opportunity to do this appropriately for your use case, your data model in your environment. Now, if you don't want to do those things, you can take advantage of React data types. And the only difference between a data type and a regular KB is that we do a predetermined merge strategy. So, for example, with a distributed counter, the merge strategy is simply additive. Add all the integers together. With a set, it's a little bit more interesting. The set is a distinct union. So every member of the set is distinct. And when you have two divergent sets, you put them together and you find the union between them. So, and then the others have other pieces as well. But this is generally our approach, and we make these capabilities available to you, the developer. But getting back to our search component, our whole product catalog thing, how do we do search? Well, we made the decision.
It's not for about 15 minutes.
Thank you. We made the decision to not be a search company. So we took a look and we said, hey, what's out there? Well, it turns out Solar is out there. And Solar wraps Lucene. In the previous conversation, there was a question at the end about Solar and Elasticsearch. Solar and Elasticsearch both wrap Lucene. Lucene is the actual search engine. It's the predominant open source, full text searching solution. There's basically no competition to it. Solar and Elasticsearch are wrappers to Lucene that make it easier to work with Lucene and then provide additional capabilities and functionality. But as far as the core searching technology, they're both, lowest common denominator is Lucene. So these are some of the only interesting things that you can do with it. And once you bring that kind of technology into your environment, let's look at what that flow can look like. And in fact, is the way that some of our customers have done these things. Recall I said, don't replace your relational systems if you can avoid it. Simply augment the technology stack. So in this kind of environment, you maintain your relational product catalog and the pipeline that feeds it, and all the legacy fun stuff that's wrapped up in that bundle. And you put a little imaginary wall. And then you use the 3 favorite letters in any DBA's kind of bag of tricks, ETL. And you start lobbing data over the fence. And there are many different ways to do this, but the bottom line is you push it to some kind of middleware. Let's talk about just how you do this in this hypothetical environment. Not so hypothetical environment, because people actually do this. You have some kind of middleware. It takes each of the rows from that CSV. It turns it into JSON. The JSON gets put into RIAK. So the actual products are stored as JSON manifestations in RIAK, are then indexed via Solar, and all of those downstream applications, the access by mobile, the access by web, quality assurance, operations, all these fun things, they all get that information from the RIAK Solar combination. This is an interesting kind of pseudocode design pattern that you can then employ if you have this kind of technology. And actually, you don't even need it for this technology. You could also employ this with regular SQL as well. The cost in any searching environment is actually executing the search. And whether it be relational joins or Solar index lookups, there is a cost associated with it. So here's the kind of waterfall design pattern that some people are using to pull this off. How you search Solar is through a URL, and you give it in the bold at the end over there some kind of searching parameter. You take that search parameter, everything to the right of the question mark in that URL is considered the query string. You take that query string, you hash it, and hashing anything gives you a fingerprint, some kind of number. MD5 hash, SHA-1, etc. What you do is you interrogate. But what's the output of Solar Query? The output of Solar Query itself is a JSON blob. So you look for that JSON blob internally in RIAK as a key. Where is it? So let me just get it. So you look at the query cache bucket, you look for that fingerprint. If you get it, return it. If you don't get it, then execute the search. And when the search completes, cache the search and send it back to the customer. So that's just a generic design pattern on how you can do some of these things. And the reason you would do this is to amortize the cost of the Solar query over the lifetime of your data. And in this case, we control the lifetime of the data because you control the frequency of the ETL. But wait, more things. So how do you get this beyond just searching? So I mentioned, the title of the talk is RIAK NOSQL and Redis and Spark. And recall I mentioned we're not one piece of tooling that can solve all the problems. Our first integration, major integration, was with Solr. And we used Solr because it's the leader in full-text searching. But we took a look and we said, what is popular? What are other people using? When I personally go and talk to customers, what are they using that complicates their installation, their operational stack? And Redis and Spark were two things